It is my great honor to introduce the last speaker for today, Andreas Wallraff. I'm also very proud to say he was my own tutor back at my time at ETH, and also the Past Brothers tutor back at their time at ETH. He's truly a legend of the quantum community. Where has he not worked? He's been to Paris and Yale and ETH and RWTH Aachen right now, obviously working as a full professor at ETH. He's the founding director of the Quantum Center at ETH Zurich, a group lead at the Paul Scherrer Institute, and if I went on, it would be frankly too much to list. He's a seminal person in the world of all things superconducting qubits. You just missed his talk about quantum error correction, where his group was the first group to actually realize the surface code on 17 qubits at ETH just 2 years ago. Something like 2 years ago. So he's definitely one of the greats, and it's my great pleasure to announce Andreas Wallraff.
So thank you very much. I hope that you guys hear me online. Otherwise, send a message to one of the organizers, and I'll step closer to that camera maybe. Also for everyone online, unfortunately, I can't point at the slides, or maybe I can try from here. This might work. Does it? No, it doesn't so far. At least it's okay. Good. So I can either look at. So that's the problem. So the no complaints, but the way how this should work is so you should just connect the computer to the presenter and then share, or so then you don't have this. But okay, well, you guys can download the slides for this presentation by scanning this QR code. Has anyone tried already? Does it work? It works. Good. Excellent. So I'll leave this on for a second so that you can do that. Everyone who wants to download the slides and make comments on it, you put there. Good. So I'll use my time to say a few words about how to do 2 qubit gates. I'll maybe discuss the basics. This is not supposed to be kind of a state-of-the-art 2 qubits. I might comment 2 qubit gates. I might comment a little bit on that throughout my presentation. So I'll also start a bit walking you through one of the devices that we've used for a few of our experiments, which is the one that you see on this title slide. I don't know. I see some of you were at some of you might be swapping between the beginners and the advanced track, and so I'll discuss this device a little bit with you. So for those who have seen it already in the discussion of the quantum error correction work that we did, that you'll get to ask a few more questions about it now, and otherwise. So maybe also to. I'll ask the same question as I had asked before, just to get a little bit of an idea of what your background is. So who of you is a theorist? A few theorists. Who of you is an experimentalist? Experimentalists outnumber both. So who does both? Some of you who works with superconducting circuits, theory or experiment. Who doesn't? Or who has no experience. So okay, good. So this is different at the beginner's track than at the advanced track. So that some of you know less. So I think this is my talk is angled at my presentation is angled at covering some of the basics for gates. And I would also encourage you to ask as many questions as you like, because this is for you to take as much as possible out of this presentation rather than for me to go through my material. Okay, so there's 2 qubit gates with superconducting circuits, and the names listed here are the current members of our lab at ETH Zurich. Okay, so this is a picture of a device with 17 superconducting qubits. It's an actual photo of the real device, and you see apparently the dicing saw wasn't super well adjusted, so there's some chips, some clippings at the edge of the chip. but otherwise this is a real picture of this, or it indicates that it's a real picture of this device. It has 17 superconducting qubits. So if you look at the different colors, the light gray is the metallization on the chip. In this case, this is niobium as a superconducting metal. The darker gray is the substrate, which is silicon in this case. And what you mostly see at this scale, there should be a scale bar, is at this scale, sort of the chip size is roughly 14 millimeters by 14 millimeters. The now yellow colored structures are part of the superconducting qubits that we use. In most of our experiments, we tend to use transmon qubits. So those are essentially qubits in which a Josephson tunnel junction or a pair of Josephson tunnel junctions forming a squid are shunted to ground by a capacitor. And this capacitor on these devices is formed by these yellow structures. And you see 17 of those on this chip, and they sort of sit in this square lattice arrangement. And it's 17 qubits on this particular device because that's a good choice if you want to do some quantum error correction and you would wonder where this weird number of 17 qubits comes from. And so in the surface code in quantum error correction, if you use 3 times 3 data qubits, then you can store logical information in these 9 data qubits. And you use an additional 8 data qubits to measure whether errors occur on these 3 by 3 data qubits. So 8 plus 9 is 17, and so therefore you end up with a device that has 17 qubits. So every one of these yellow structures which form the capacitor, so this is essentially a capacitor to ground. So this has capacitance to all the other metals in this 2-dimensional plane. And it has relatively little capacitance to anything else that might be in your chip package. So maybe some packaging in which your chip is housed inside of your dilution refrigerator. The capacitance is really dominated by capacitances which lie in the plane. And so then every one of these superconducting qubits is kind of shorted to ground through a pair of Josephson tunnel junctions that for this particular qubit that I'm pointing at, and that unfortunately online you can't see, is the 2 tunnel junctions are located in this location here. So then every qubit has a coplanar waveguide that reaches up to that particular qubit. So these coplanar waveguides are colored in pink here. It's an open-ended coplanar waveguide transmission line. So if it's open-ended, it will have an electric field antinode at its end. So the electric field will be maximum. And that electric field will actually couple to the island of the transmon qubit. And this coupling allows you to drive transitions in the transmon qubit from its ground to its first excited state. So then, in addition, every one of these superconducting qubits of the transmon style has a so-called magnetic flux line. Those are shown in green here. They're also coplanar waveguides. But instead of being open-ended near the qubit, they're actually shorted near the qubit. So they're terminated into the ground. So if you apply a voltage pulse to it, it will run a current into the ground at the end of this coplanar waveguide. And this current will create a magnetic field. And this magnetic field will thread the squid loop, which is part of the transmon qubit. And when that happens, you can actually tune the transition frequency of the transmon qubit. And tuning the transition frequency of the transmon qubit is essential in realizing 2-qubit gates. So in this particular architecture that we use in our lab, gates are initiated by tuning 2 neighboring qubits, which have 2 different transition frequencies, into resonance with each other using these flux lines. And so when the 2 qubits are in resonance with each other, the 2-qubit gate acts, and when they're detuned from each other, the 2-qubit gate is in good approximation turned off. And how off the 2-qubit gate is, it depends on the detuning between the 2 qubits. Good. The coupling between the neighboring qubits gets mediated by these blue coplanar waveguides. So there, you can look on the scale bar. So there may be 3-4 millimeters in length. So at this 3-4 millimeters in length, they have their first electromagnetic resonance, maybe at a frequency of around sort of somewhere between 20 and 40 gigahertz or so. So these the interactions between neighboring qubits, they're not mediated by exchanging sort of real resonant photons with each other through these waveguide resonators, but the interaction is essentially mediated by virtual photon exchange through these resonators. So the qubits are detuned from the resonance frequency of the resonators. There's a question
online. Are the perforations in the ground claimed to prevent vortex trapping?
So the question is, what is all these little dots that you see? And the little dots is you actually look through the metallization film onto the substrate, and indeed they're there actually to trap flux, trap magnetic flux. So if you have a thin film superconductor, or ideally if you have a bulk type 1 superconductor, you would expect when you apply a magnetic field, it will expel all that magnetic field up to a certain critical field, and then at that critical field, all superconductivity actually should collapse. But if you have a thin film, if you surpass the threshold field, actually magnetic flux will penetrate in form of superconducting vortices into these films. And then when currents run through these films, these vortices can move around. And if the vortices move around, they will create dissipation because they move with themselves like a bit of a normal metal material or so, which includes normal electrons, and that will create loss. And these holes are expected to contribute to trapping of these vortices. And there were experiments that looked at this vortex trapping physics and the dissipation they induce, but I'm not sure whether there's like really good experiments like in larger scale devices that really show the performance with and without these holes. So I think there's good reasoning why you might want them to be there, but could be like now, and like, would I do a similar experiment without these holes? How different would it look like? It's kind of not so easy to see. Maybe Daniel can comment on later whether their devices have such flux trapping holes or not. I think it's a bit of superstition that is involved in having these. I think, despite the fact that like the mechanism that I mentioned, it's clearly there and it exists, and you can suppress it by trying to trap these forces. Good, and then you see these red resonators. So and Daniel has talked about readout of superconducting qubits. So these are lambda quarter resonators that are strongly coupled to these qubits, and you look at the frequency shifts of these resonators when the qubit changes state, and from this dispersive James Cummings Hamiltonian, you see that the resonator inherits a qubit state dependent frequency shift that you can read out and to determine with good fidelity or low error the state of the qubit. And then for having your readout fast and high fidelity, what you want is you want the readout resonators to be strongly coupled to your qubits. Unfortunately, when you have a single readout resonator strongly coupled to your qubit, even if the qubit is detuned from that resonator, so for this readout, you typically have the qubit detuned by quite a bit from these readout resonators, but still at this detuned frequency, it partially hybridizes. The qubit hybridizes a little bit with this readout resonator. And so say with a small percentage fraction, the qubit excitation is actually an excitation in the resonator. And if that excitation in the resonator would decay, then the qubit would also decay through this mechanism. And so this decay is called the Purcell effect. And for example, if you want to build single photon sources, if you have a quantum dot and want to build a quantum dot single photon source and you want to get many photons out, you actually use this Purcell effect to get the photons out quicker out of your quantum dot than without having such a resonant feature. But here it's sort of something unwanted, and you would want to suppress that Purcell decay. And therefore, there's another lambda quarter resonator that is resonantly coupled to the readout resonator, and that essentially suppresses the Purcell decay. And one of the ways how to think about it is, say if you have a single resonator coupled to a qubit, this resonator has a Lorentzian line shape. And when the qubit is detuned from that resonator by some amount, or so the probability with which that qubit will lose its excitation into that resonator has to do with kind of the density of states for photons in this resonator, and it drops off with this Lorentzian line shape. And if you couple a Purcell filter to that readout resonator, you can make that line shape actually, instead of falling off with the square of the detuning, it can fall off with a fourth power of the detuning. So the effective line shape gets more narrow and the qubit decay gets suppressed. So that's why these Purcell filters are there, to allow for fast readout while maintaining the qubit. And then
What is your coupling to the line reflected forms?
Okay, yeah, I'll maybe come back to that in a second. So so this is a zoom in. So when you zoom in on one of these qubits, it looks like that. You see the yellow capacitor. So here you see the squid. The two channel junctions are in these two locations here. There's this loop that is formed by the squid. There's this green line that gets shorted to the ground that has a current passing through it and inducing a flux here. And I'll zoom in on that a little bit. And so then you have various capacitive contributions to the coupling. So this line, the yellow part couples to the ground plane. The yellow part couples to the readout resonator for enabling readout, and then to these four couplers around the qubit that couple one of these qubits to their four neighbors. And there's a little bit of capacitance also in these Josephson tunnel junctions to the ground. And that probably in one of your lectures today, you heard about the transmon qubit, and it has two parameters that set its properties, which are the Josephson energy and the charging energy. And the charging energy is set by the total capacitance of this yellow island to ground, and the sum of these capacitances sets the charging. Okay, if you zoom in even a bit further, yeah, so I indicate here the two Josephson tunnel junctions again for you, and I outline this black line and the green shaded arrow, the loop of this squid, and the current flowing through this green line induces a magnetic, or creates a magnetic field, and then the product of the magnetic field and the area of this light green shaded squid loop gives you a magnetic flux, and the magnetic flux tunes the Josephson energy of the transmon qubit. And so this mechanism now allows you to, if there's zero current through this line, the transition frequency is highest, and if you send a current through the line, the transition frequency actually drops. And this we use to tune neighboring qubits into resonance with each other. So here's the picture of the full device again. And so there was now this question about it. So there's these purple lines are feed lines for the readout. And so before I mentioned that every qubit has an individual charge drive line and an individual flux drive line. But then the qubits are, the readout of the qubits is frequency multiplexed. So there's multiple readout resonators hooked off this dark purple readout drive line. And And the frequency selectivity comes from the fact that now every qubit has a readout resonator at a slightly different frequency, so that you can sort of frequency division multiplex this readout. And essentially you can send a pulse into this feed line that is in some sense monochromatic, where you have a pulse that targets every individual readout resonator, and the width of that pulse in the spectrum needs to be smaller than the separation in frequency space of these different readout resonators from each other. And so now there was a question like, why does this capacitor here look the way it looks? And so a standard way to make a capacitor is you could just have two coplanar waveguides face each other. And then if you want to increase the capacitance a little bit, you could maybe expand the coplanar waveguides a bit in this area, or you could make these interdigitated capacitors, or in the way that it's realized here, it's sort of this thing that we call sort of a hugging capacitor. So where one of the electrodes has kind of a rectangular shape, and the other electrode sort of grabs around that rectangular shape. And this is essentially there to control the capacitances of the different elements with respect to each other, and could have also realized it in a different way. And the typical thing that one does is one creates sort of planar structures. And so you could imagine that you could, if you want larger capacitors, you could also make overlap capacitors. But the problem in overlap capacitors is the electric fields are typically much larger. And so the dielectric that you would then place in between your two electrodes is usually much more lossy than the dielectric of the substrate that these superconducting metal structures are on. Yeah? And therefore, most of these structures are planar. So there's another
two
question.
questions. First one is, how do we deal with cooling to maximize qubit data? And the second is, what component would allow us to perform multiplexing in frequency?
So this whole chip is cooled to the lowest temperature that your dilution refrigerator can achieve. So that's usually say around 10 millikelvin or so, 10 thousandths of a degree. All the components on the chip are all superconducting. So when you apply all of these control pulses, the actual loss on the chip is very, very small. The heat that gets generated by applying these fields is quite small. So it doesn't physically heat up a lot in a way that you could actually measure a temperature or so. I mean, things that could happen is that maybe you break some Cooper pairs and excite quasi-particles if you're not careful. But otherwise, heating is not really a problem, despite the fact that your dilution refrigerator has a small cooling power at these base temperatures. And then the other question was about what property allows frequency multiplexing, and the frequency multiplexing comes from this fact that you frequency division multiplex. You essentially, the readout resonators that you pick up here, they're designed to be at different frequencies, yeah, and the typical thing that we would do. So and that's maybe something that Daniel had talked about, is, say, if you have a detection bandwidth of a gigahertz or so, then you would space out for a single detection line, your readout resonator is kind of, say, at a spacing of maybe 100 megahertz or 200 megahertz in frequency space. And then your control electronics can target these readout resonators at around, say, 4 to 5 gigahertz, or maybe 7 to 8 gigahertz, which are spaced out by 200 megahertz from each other. And that allows you to frequency division multiplex and address the readout in resonators individually. And sort of an interesting question to work on is how to bring more multiplexing technology to these types of devices, so that you can control more qubits and read out more qubits with less wiring. Okay. So maybe are there any other questions about this device? No.
And notice that in the bridges, you go back.
Yeah.
Approximately the bridge was used in the center But on the other lines, the bridge, or no, the back one,
You know,
they may not be. Looks like the bridges were used to tie the grounds together, yeah.
So what Daniel is referring to is here the couplers between qubits. They're connected through these air bridges, and the grounds are connected through in the ground plane. And sort of here it's done in the reverse way, and you could ask yourself why is that? And so we actually made devices in both ways. So instead of having like the ground being connected, so maybe for those who don't know, it's sort of these air bridges, actually they are freestanding. So there's vacuum between this piece of metal and the piece of metal underneath. So they're not in contact. So the air bridge crosses across this wire that runs underneath it. And that allows you, even in a nominally two-dimensional chip, to create some 2.5D structure. And we've made devices of this sort where also these lines were going through in the ground plane metallization, and we made an air bridge across. And this version, and it essentially didn't make a difference. So there was a time when we were a bit worried about the reliability of our air bridge fabrication process. And in these transmon qubits, the parameters that they have in the end, they rely a fair bit on how displacement current, say if the transmon qubit changes state, the charge distribution on this capacitor will change, and there will be image charges in the ground plane around it. And when the qubit changes state, this image charges redistribute, and there need to be currents that flow. And for example, if there was no connections in these ground planes, then the currents would flow quite differently, and in particular, they would create extra inductances, and those will change the parameters of these qubits. And so when these were designed, we figured that it was more reliable in this way. But in the end, it doesn't make a big difference. Also, for example, if your air bridges, say if they were not connected very well to their ground plane, say if there was a little bit of resistance, then these currents would flow through this resistive part. And that would matter more in the screening areas of the qubits than it would matter in these couplers, because the couplers are used non-resonantly, and there the loss matters less than the loss associated with the qubits. And there's lots of things like that when you stare at these devices, and if you're allowed to stare at people's devices, where you could ask yourself questions about why is it like that, and what was the thinking about it, and how the thinking develops through time with better and better understanding these different elements on these devices. Good. The other thing with this delay is that this slows me down talking. So this is usually for lectures, it's probably a good thing rather than a bad thing, but it also makes everything a bit more sluggish. So no more questions here.
One more. What ideations could be made while developing circuits for qubits?
What
Ideations? I don't know.
I don't know what that means. So
Neither. Does anybody know what idealizations maybe? I don't know.
Okay, there's okay. I don't know what you'll learn a lot more about designing these circuits in the coming days.
Changing things.
So our lab we have our own software. We have our own software suite to both design these circuits, to make sort of the physical designs, what they look like, and also to simulate their properties. And there's, I think, everyone who needs to design bigger circuits needs something like that, yeah, because you will not draw this by hand. No will you fully simulate it by hand, and neither can you fully do a finite element simulation of the whole thing and learn something from it. So you need to develop a strategy for how to address questions like this. And I think this is a large part of what this course will be about, and you'll learn about that in the coming days. And we have our own set of tools for that, but I don't think that we do anything that is particularly magic. I think the best strategy in this will be to understand components. So there's many components, there's capacitors, different elements, and you want to understand all the capacitors, all the elements well enough. And then from these understanding of the individual components, you build a more complex circuit from which you still hope that you understand everything about this more complex circuit based on the understanding of the individual components. Yeah, and typically what then happens is you make this big device, and something is not quite the way how you imagined it to be, and you're trying to understand why that is, and then refine your model. And if you make this more and more systematic, yeah, you end up with maybe a better software suite to design these chips. And then once you've designed them and made them actually perform the way how you expected them to perform. Yeah? And that's one of the challenges in doing this well. So this is how this proceeds. Good. All right, so I'll tell you a little bit about 2-qubit gates, but I'll also give a little bit a reminder about single qubit gates. And as I said, you should really ask anytime any questions that you have. All right, maybe for the reminder of the single qubit gates. So here you see a piece of that chip that we've just discussed. And the first thing that you do when you get going is you try to apply microwave tones to your qubits to find their transition frequencies. Then you make short pulses of these microwaves to prepare states. And you would do so usually after you've started sort of in a spectroscopic measurement to determine what the qubit transition frequency is. Yeah? So you would use Daniel's readout, and then you have a microwave tone that you scan across the qubit transition frequency. And when the microwave tone is resonant, you see the qubit going from the ground state into on average mixed state, which you can then determine in your readout signal as the resonance frequency of your qubit. And then you can use that resonance frequency and control the amplitude and the phase of that microwave tone and its duration, and do things like Ramsey measurements, Rabi oscillations, and Ramsey measurements. And when you vary the pulse parameters like their duration, amplitude, and phase, yeah, you can go and prepare different qubit states, which you then can characterize with using quantum state tomography. So maybe I wonder, so Daniel, have you talked a little bit about quantum state tomography in your presentation? No, does everyone know what quantum state tomography is? Like if you had any form of introductory quantum information science lecture, you've probably learned about it. Who doesn't know what quantum state tomography is? One. Everyone else does know. So does someone want to explain it since you all know it? Okay, so maybe one. Let me say. Okay, I'm trying to point at things which doesn't work. So you have one of these superconducting qubits here. You apply a microwave pulse through this pink line to the qubit to bring it into an excited state. And then you would read out its state, and with the readout that Daniel has explained to you, you measure the sigma z expectation value of your qubit. Yeah? So you only project your qubit state onto the z-axis of your Bloch sphere, and this is clearly only partial information. So to get the x and the y components of your state vector, you need to measure the x and the y components. And if your measurement setup can only measure z components, then the thing that you do is rather than building a new measurement setup, you rather apply a pi half pulse to your qubit about either the x or the y axis, which then turns what was the x component into the z component, which you can now measure, or the y component into the z component, which you can now measure. And if you combine like 3 measurements of you do nothing and measure the z component, you turn the x into z and measure it, you turn the y into z and measure it, you can get the x, y, and z components of your qubit states. And then if you do that, you can look at rotating your qubit state vector on the Bloch sphere. And so there's a little animation here. So from a measurement where essentially the amplitude of a pulse applied to the qubit was varied, and for each one of these amplitudes, the qubit state vector was then measured using this quantum state tomography. And when you do that, you can plot your state vector on this Bloch sphere. or alternatively, when these three representations have an equivalent information content, you can look at the real and imaginary part of the density matrix, or you could also represent that same state vector as the expectation values of the Pauli X, Y, and Z operators, which are just the expectation values of the Pauli sigma Z, sigma X, and sigma Y operators. And you can do the same thing. So say if you want to rotate your qubit state vector about an orthogonal axis, the only thing you do is you shift the microwave pulse in phase that you apply to your qubit by 90 degrees. And that phase shift actually now rotates the qubit state vector not about the y-axis, but about the x-axis. And the tomography techniques allow you to reconstruct the qubit state vector with all of its components. Okay, and this so there's these gates. So if you do it on this level, you can maybe determine whether the gate works on the 1% level, on the 1% error level, and if you want to determine higher gate fidelities or lower gate errors, you need to resort to more sophisticated techniques. And one of these techniques is so-called randomized benchmarking. And in randomized benchmarking, say assume your error was very small, like if you have tuned up your gate very carefully, your error is maybe 10 to the minus 4 or so. And then on the 10 to the minus 4 level, to do your measurement accurately enough to recognize that error will be difficult. So instead, you repeat your gate a large number of times. So you do 10,000 times this gate with 10 to the minus 4 error, and then the error accumulates. And you could look at this accumulated gate error and try to extract the error per gate from that. And that's what's called randomized benchmarking, which maybe you'll hear more about at this school. And if you really take care these days, I think you can, like, to get a gate error of maybe a single qubit gate error of about 1% is not really hard. So it kind of works out of the box. And you can, if you take some care in calibrating everything, you can maybe get 10 to the minus 4, and probably, I don't know, I Google what you probably have a few times 10 to the minus 5 now when you really take care for single gate errors. Good, and so this is supposed to be about 2 qubit gates. So I'll tell you a little bit about how you realize 2 qubit gates. So if you look at a coupling Hamiltonian between 2 different qubits, it's written down here in a specific form. So sigma 1, sigma plus, and sigma minus are the qubit raising and lowering operator. So sigma plus operator brings the qubit from the ground state to the excited state, and sigma minus brings it from the excited state to the ground state. And in this coupling Hamiltonian here, this factor J gives you the coupling strength between the 2 qubits. And essentially, when one qubit goes from the excited state to the ground state, the other qubit goes from the ground state to the excited state. And these qubit raising and lowering operators you can express in terms of the Pauli X and Y operators. And so the question is, how can you realize this coupling that gives rise to the 2 qubits exchanging states between each other? So you could either directly capacitively couple the qubits to each other, so 2 transmon qubits with a capacitor between them. Or you could, for example, couple both of your transmon qubits to a resonator or resonant mode, and you can have the resonant mode exchange the coupling between the 2 qubits. And so one of the ways how you then induce gates between the qubits could be by tuning the qubit transition frequency, as I've mentioned to you. So if the qubits are detuned from each other, the coupling is suppressed, and if they're resonant with each other, the coupling is stronger. And that's the type of qubit control that I'll be discussing with you today. But there's also other ways how to do 2 qubit gates, for example, by using microwave drives. Or if you have tunable couplers, so couplers whose coupling strength can be modulated in time, you can also use parametric driving of these tunable couplers to mediate interactions between qubits. And here's a few references for these different tunable coupler approaches. But I'll talk about these kind of static couplers. And the state-of-the-art tunable couplers, for example, those that are used by Google. The nice thing about those is that you can dynamically tune the size of this coupling strength J, so the speed at which qubits exchange the excitation with each other. And that's good because if you can set J to 0 or so, the coupling is off. So your 2-qubit interaction is essentially off or 0. And you can also be more aggressive in having J large to get fast 2-qubit gates. So this is nice to have. So this slide discusses a little bit here on the left-hand side. You see a measurement of a qubit transition frequency versus magnetic flux on this top axis here, applied to the squid loop of the trans-1 qubit. And what you can see is that you can, for this particular device, tune the transition frequency of the trans-1 from a minimum value of like 4.5 to a maximum value of about 6 gigahertz. And so that's the range in which you can tune your frequencies of your trans-1 qubit. So if the two tunnel junctions had exactly the same size or the same Josephson energy, then actually at this particular flux, at plus or minus half a flux quantum, the transition frequency would go to 0. And if the two tunnel junctions are different in size, have different Josephson energies, this asymmetry will actually determine the lowest frequency that you can reach. And actually for coherence of the trans-1 qubits, it's good to have some asymmetry in your junctions so that the transition frequency doesn't drop off to 0 if you're close to this flux 1/2 bias. So that allows you to get better phase coherence in your trans-1 qubits. And now you need this information here because when you apply flux, this will control the qubit transition frequency. And as I said, the control of the qubit transition frequency determines the action of the gate between neighboring qubits. Okay. So in the early days, when one did these 2-qubit gates, one was thinking about the 2 qubits to be coupled with some detuning from a resonant mode, and that's the picture that is shown on top here. So there's a trans-1 qubit on the right, a trans-1 qubit on the left, and they both couple to the far ends of a resonator whose lambda half length determines its resonance frequency. So the physics of the structure, a resonator coupled to 2 qubits, is described by this Tevis-Cummings Hamiltonian, which is written down there. So did you discuss today the Jaynes-Cummings Hamiltonian, a little bit of circuit QED? You've done probably, I guess. Yes, okay. So the Jaynes-Cummings Hamiltonian is very similar. It's the same Hamiltonian just for a single qubit. So without the sums, so when you just would consider like 1 qubit. So you can write down the same Hamiltonian for multiple qubits. And that could be, the qubits could have different coupling strengths to the resonator. The qubits can have different transition frequencies individually. So here's an energy level diagram, which is from this kind of oldish paper that you see cited there. And in this particular energy level diagram, like the 2 lowest states are the ones associated with no photon in the resonator and 1 photon in the resonator. And here the situation is considered that both qubits have transition frequencies that are higher than this coupling resonator. And the 2 qubits in this case are detuned from each other. So that the left qubit has a lower transition frequency than the right qubit. And the 2 qubits have coupling strengths G1 and G2 between the qubit and the readout resonator. And they have individual detunings of the qubit to the readout resonator delta 2 and delta. So if you look at this Hamiltonian here, you can sort of transform it into a form that is useful to understand the coupling. And here this transformation has been applied. And here in this part of the Hamiltonian, you see that the terms that actually allow you to perform this dispersive readout that Daniel has discussed. So the terms here, this A dagger A sigma Z term is the one that where the qubit gives a shift to the resonator frequency, or reversely, photons in the resonator exert an AC Stark shift on the qubit. But if you have multiple qubits, there's this extra term here, which has exactly the form that I've mentioned before, where you have this coupling strength and this sigma plus, sigma minus operators, which exchange the excitation between the two qubits. And sort of the interesting bit now is if you bring the two qubits into resonance with each other by tuning their transition frequency, then actually they start to interact at a rate which is given by this coupling strength J. And this coupling strength J now depends on the couplings of the individual qubits to this coupling resonator and their detuning between the qubit transition and the resonator. And if you put typical numbers, you see that you can get coupling strengths anywhere from a couple of megahertz to maybe a couple of 10 megahertz. And so what you then do to switch on and off this coupling is to actually tune the qubits into resonance with each other and give them a large effective interaction strength, or suppress that interaction by detuning them from each other. So here's a picture of what that looks like, and actually one of the first experiments in which this was realized, and this was done by Leo Di Carlo at Yale. So on the top here, you see like the Wheatley line as a resonator, and on the right side there's a blue qubit, on the left side there's a red qubit. And here the left red qubit stays constant in frequency, while the right blue qubit gets tuned by applying some magnetic field to that qubit. And when the two qubits get into resonance with each other and you just do spectroscopy, you see that there's a splitting, like there's an anti-crossing. And the size of this anti-crossing actually relates to this J term in your Hamiltonian. So that's from this you can read off the rate at which the qubits exchange their excitation with each other. So this is the avoided crossing between kind of right qubit in the excited state and left qubit in the excited state. And when you tune that right qubit down in frequency into resonance with this resonator, you see its vacuum-Rabi mode splitting. That's when that qubit exchanges its excitation with the resonator. So that's the splitting here sets the size of this G1 or G2 coupling strength that was in this Tevis-Cummings Hamiltonian. And so that interaction here at this anti-crossing you can use to perform a so-called I-swap gate between your two neighboring qubits, and sort of in a kind of in an energy level diagram, you could imagine it this way. So there's 4 states, the 4 different combination of qubit basis states that are indicated here. You prepare one of the qubits in an excited state, you tune it into resonance with the other qubit, then this interaction J leads to an exchange of the qubit state, of the qubit excitation from the left qubit to the right qubit, and then twice the amount of time the excitation oscillates back to the original qubit. And so this transformation, because it creates this phase factor of I in front of the 0-1 state, is also called an I-swap gate. And the time that it takes relates to the coupling strength. So if you have a large coupling strength, you can get a short time at which the two qubits exchange their states. And so this is a gate that sometimes is realized with superconducting circuits. And how it works, you can try out by preparing the individual qubits in their initial states and then running this I-swap gate. and at the end performing tomography on both of the qubits in the way that I had mentioned before. So there's a question.
Yeah, regarding the, I guess, swap, as you just said that, right? The stronger the interaction strength, the faster you can technically swap.
Yeah.
If you want to ideally, maximize how fast you can swap, why don't you just go stronger and stronger in coupling? I guess because the, some form of leakage or some form of decay is going to just enhance, right?
So what limits this J? So there's various sort of size of the coupling strength, and for example, if you have a coupler that can be tuned, where J can be tuned, I think you can try to be large when you want the gate to act. So the gate only turns off proportional to the detuning. So if J is fixed or so, and you have some finite detuning, which will always be the case because one qubit stays at the fixed frequency and the other one can only go so far away. If you tune it down in frequency, it can go to its minimum value. If you tune it up, it can go to its maximum value. And so your effective J in this nominal off state will still be finite, and this will lead to some so-called finite ZZ coupling between your two qubits. And so when you hope your gate is off, it's not sufficiently off, and so it's hard to correct for that. So you don't want to do that, and the way out of it is to use devices which have a tunable coupler. And for example, to get a tunable coupler, there's various ways how you could realize this, and I'm sure it will come up in one of your other talks. Yes.
For the swap interaction, I understand the qubits are first in the idling state, it's tuned by quite a lot. And then when you activate the I-swap, you tune them sort of exactly at resonance. But if you first condition that they will be along that frequency trajectory, there's the 1102 resonance condition. So I'm wondering, is that a problem that you're actually crossing through that?
Okay, so maybe I'll show this energy level diagram on one of the later slides, and maybe we can discuss it then. Okay, so here's a diagram which shows how you could change the qubit transition frequency in time. So an additional aspect that matters that I haven't mentioned yet is every time you change the qubit transition frequency, also you effectively act as a single qubit Z rotation. So for example, you do a Z gate. So X and Y gates you typically do by applying resonant microwave pulses, but Z gates you do by tuning the transition frequency. And it's essentially varies if you change the qubit transition frequency in its rotating frame, it accumulates a phase or so, and that acts like a Z gate. And this you need to compensate for. These are single qubit gates, and therefore in this kind of pulse diagram, there's not only a time where the two qubits are in resonance with each other, but there's also a time where they spend some time at some finite detuning, and those get controlled to make sure that the single qubit phases are multiples of 2 pi, so that you can forget about that. Okay, so there's a little picture of what this could look like, and maybe I'll just run this for the fun of it, but not discuss it much further. So this is the two qubits which you see in their individual block vectors, but the individual block spheres clearly don't capture all the 2-qubit physics. So if you want to have the 2-qubit physics taken into account, you need to measure these all the different combinations of Pauli operators for the 2 qubits, which then show you all the correlations that this interaction will actually generate. And for a specific period of time, these interactions then create entanglement between the 2 qubits. Maybe let me try to find those. So for example, at this location here, so you have maximum entanglement between the 2 qubits. So here you see like when you have one qubit operator being the identity and the other operator being X, Y, or Z, and the same for the other qubits, you find that all the single qubit expectation values are 0. Yeah, so they could as well be in a fully mixed state. But if you then measure the expectation values of X, Y, and YX and ZZ, you see that they are finite. Are either plus or minus 1, and this is typically the indicator then of an entangled state that got generated. Okay, so we've done experiments which looked at that, and these are also kind of quite some time ago. But the actual gate which we now mostly use and that gets widely used in superconducting circuits still is not the gate that operates between 0, 1 and 1, 0, which was asked about just before, but a gate that makes use of these higher excited states, 2, 0 and 1, 1, which are shown there with a blue arrow. And so they're essentially the same interaction or the same style of interaction creates a coupling between the two qubits, but that coupling is now a factor of square root of 2 larger than otherwise. And that's essentially related to the matrix elements in the higher excited states of this qubit. And so this coupling between 2, 0 and 1, 1, you can actually use to not do an I-swap gate, which swaps the two states of the qubits with an additional phase factor, but to do a so-called controlled phase gate. And there's another question.
Yeah. From online audience, during the excitation swapping between two qubits, would one of the qubits decay to ground state?
This would be a decoherence mechanism, yeah. So the qubits will independently decay to their ground states. So this is always possible, and that would be visible as an error in your 2-qubit gate. But otherwise, the coherent interaction, obviously, it oscillates the qubit through the ground state, but not through a decay mechanism, but by this exchange interaction. Okay, so here's this question that then was asked about before. Okay, I see it's not really on that slide either. So before we talked about this 1, 0 and 0, 1 state going into resonance. So now for this particular version of this controlled phase gate, you look at the interaction of one of the qubits being in the second excited state and both qubits being in their first excited state. So there's this crossing here. And at this crossing, the same coupling interaction that I mentioned leads to a hybridization that essentially through the same fundamental mechanism you can use to create a 2-qubit gate. And the main difference now is that you actually make use of a second excited state of one of the qubits. And that actually creates a different set of phase factors for your individual qubits. So when you would zoom into this area where the two states, the 2, 0 and the 1, 1 anticross, you would see that there is a small splitting, and the small splitting has a square root of 2 coupling factor that I mentioned to you before. And so this is actually a quite popular gate, and when you control the time that one of the qubits spends at this interaction region, yeah, you can create a phase factor of pi and get this controlled phase gate. And so here's some experimental data that Leo Di Carlo took. So you have this 2, 0 state and the 1, 1 state, and this is like measured data on this anti-crossing. And it's about 160 megahertz. And here's another picture of what this looks like in an energy level diagram. So this is the 0, 1 and the 1, 0 excitation manifolds. And this relates to the question that was asked, and the 1, 0 and 0, 1 would anticross somewhere here, while the 2, 0 and the 1, 1 would anticross up there at a different value of the magnetic field applied to one of the qubits. It's time to wrap up since everyone's leaving. Yeah. Not my fault, I would say. We've started a bit late. But okay, still time to wrap up and look forward to the beers, which I also told. What's my time? So my Zurich time is actually 2:26 a.m. I think I've earned it here.
Oh,
And he's still coming to quantum beer, so none of this an excuse.
Exactly. At least that's what my plan was. Okay, so there's individual phase factors for the individual qubit states that have to do with the frequency changes of the individual qubits. So this right qubit, the red one, doesn't change in frequency, so no phase factor. The blue one changes in frequency, so there is a phase factor. And the thing that we're interested in, there's this conditional phase factor when both qubits are in their excited state. And the phase factor has to do with this energy difference relative to the uncoupled states. And when you now tune the interaction time at this 1,1,2,0 anti-crossing, you can actually tune it in a way that you get a phase factor of -1 from this e to the I phi 1,1. And that creates the so-called C phase gate. And so this is here, this unitary matrix with the 2 single qubit phases listed here and the 2 qubit phase listed on the bottom entry. And you tune things up so that your unitary has 1s on the diagonal and the last element on the diagonal is a -1. And this is the C phase gate that you realize, and that one can turn into a C0 gate by adding 2 more single qubit gates to it. And so here's the same diagram that we've looked at before. So if you prepare both of the qubits in the 1,1 state, you can have them interact with the 2,0 state and have this effective swap interaction that I've indicated kind of schematically here. So you let this interaction go through full cycle, and when you're back in the original state, you have accumulated this phase factor of -1. And if you think about having prepared any of the other states, 0, 0, 1, 1, or 0, 1, or so, you wouldn't get any phase factor, at least no 2 qubit phase factor, and that essentially creates this C phase unitary that I've mentioned to you. So where only the 1,1 state picks up this phase, which creates this matrix, which you can then use as your 2 qubit unitary to realize gates. And this 2 qubit gate is universal, and so you can employ it in your gate sequences. And for those of you who were at the quantum error correction talk earlier today, so this is also the gate that we've used in these types of experiments. Good, and this controlled phase gate you can turn into a C0 gate by augmenting it by 2 single qubit rotations. So if you, on one of the qubits, you prepend it with a pi-half rotation before and after the C phase gate, you can turn it into a standard C0 gate. All right, and then so there's different ways how you can then characterize this gate. You can do like an expanded version of, or an extended version of tomography related to gates, which is called process tomography. You essentially feed input qubit states into your 2 qubit gate and perform tomography on the output qubit states. And if you do this systematically, you can essentially reconstruct the action of the 2 qubit gate and characterize its quality. Or you can do the same thing that I mentioned before. You can do randomized benchmarking. You repeat these gates a large number of times in a sequence with some tricks in the choice of the gate sequence and extract the error per 2 qubit gate as well. And today, if you do this well, or so, you can get 2 qubit gate errors that are the order of 10 to the -3. Or if you work really, really hard, you can maybe approach it a few times 10 to the -4. Good. So I see the chair is standing, and I saw many of you were leaving, and I'm thirsty, and so maybe we'll leave it with that and take more questions. Thank you very much.
Anybody in the audience have a question, or go online? Okay, perfect. First question: how do you mitigate unwanted ZZ interactions due to the phasing 2 qubits are in an exchange interaction?
So what to do about the ZZ interaction, is that?
Yeah, so what happens if, how do you want to mitigate it due to the phasing when you do a Korean interaction?
Okay, so so you want the ZZ interaction to be as small as possible. So if you have a tunable coupler, you can tune your coupling to 0. If you don't, you can have a large detuning between the between the two qubits, or you can use some dynamical decoupling techniques. So for example, if you learned a little bit about NMR in your quantum information science class, in NMR, you can do quantum computing with only always on interaction. So for example, in molecules, and there's suitable decoupling routines have been developed to allow you to do that. So it's known how to deal with this, even though it's obviously better if you can tune your couplings to 0, for example, using.
Any other questions?
So for the iSwap, you showed like the 0, 1 and 1, 0 states. The interaction between them was mediated by 0, 0, right?
No, not really.
What was it?
So it's I think the so there were, okay, good, in this old energy level diagram, or in this old style energy diagram, there is a 0, 0 state, which is when all the qubits are in the ground state and the resonators are also in the ground state. So then there was also a 0, 0, 1 state with both qubits still in the ground state, but one photon in the resonator. And the 1, 0, 0, 1 states, they couple actually through the excitation in the resonator of resonantly. So it's again through this. So there's this Travis-Cummings Hamiltonian with the resonator mode, the two qubits, and the coupling between the two qubits and each resonator mode. And then if you perform this Schrieffer-Wolff transformation, you see that effectively gives rise to an effective qubit-qubit coupling. And usually, like, one way to talk about it is because the two qubits then swap the excitation not through direct capacitive coupling, and also not by exchanging a real photon through the resonator, but you would look at it as exchanging a virtual photon through the resonator. So the interaction gets mediated by the resonator, but non-resonant. And so as it's non-resonant and would not conserve energy, or so like the standard way in quantum optics to talk about it is as a virtual photon exchange.
So what is the order here of the perturbation theory or of the interaction?
It's the first non-vanishing order or so of this.
It wouldn't be second, right?
Is it? I think I would need to stare at the Hamiltonian. It's probably second order, yes.
So your Schrieffer-Wolff was the second order.
Yeah.
Okay, cool.
And the first, but it's the first non-vanishing term that you care about. And what's then? There are probably higher order terms, or so, which one then neglects.
Thank you.
No more questions. Thank the speaker again.